Alrighty, welcome back, everyone. I'd like to welcome Kathy Kha to the virtual stage here. She has been leading the cost estimation effort and has tackled some rather challenging things like, how do we model what it's going to take to run something for as long as the scientists and engineers have talked about. And thank you, Kathy, for preparing for today. The floor is all yours.
Great. Thanks, Michael. So today I'll be running through the baseline cost estimate for Interstellar Probe, or at least the status of where it is right now, how we developed that estimate, and what our cost risk analysis is showing in terms of the confidence level we have on that estimate right now. Next slide, please. Okay, so for a quick agenda, I'm first going to go over really quickly kind of some cost estimating 101. Just so we're all on the same page. I'm not really sure how familiar this audience is with kind of the tools we use in cost estimating. Then I'll go through the ground rules and assumptions that govern our estimate. So all the rules, in terms of the fiscal year and other assumptions that we've made when developing the estimate. I'll then go through the estimating methodologies that we used for the estimate. They vary based off of kind of the which one was appropriate depending on which WBS we were looking at and even which phase we were looking at. So we'll go through that after that. And then finally, you'll get your the first look at what the estimate's currently sitting at in terms of cost. And then I'll go through how we compare to other past large strategic missions and the missions that we're analogous to. So we'll look at some comparisons to New Horizons and Parker Solar Probe particularly, and then a short cost risk discussion, and then cost impacts of longevity, and then other open items that we're still looking into and working on in terms of future updates to the estimate. Next slide, please. Okay, so what is cost modeling? It's a prediction of future costs based off of historical costs. So while Interstellar Probe is going to be, in terms of phase E, something that's never been done before, and then in phase A to D, there's going to be a lot of development work in terms of testing that for 50 years and all that hasn't been built, but hasn't been done before. We do have tools to estimate those future costs, even if it's something we haven't done before. It's that's something that we're familiar with in terms of estimating uncertainty. And the last thing here too is that we don't estimate costs kind of in a vacuum. We work with the program and the team to make sure that everyone has input into the cost estimate. So we get technical inputs from the engineers, we get scheduling inputs, programmatic inputs. We have all of that reflected in the cost estimate. Next slide, please. So the three main estimating methodologies that any cost estimator is going to use are analogy, bottom-up, and parametric. So an analogy estimate is exactly what it sounds like. It's a comparison to a historical mission that's either similar in terms of architecture and hardware or in terms of programmatics. So for Interstellar Probe's case, our spacecraft hardware and architecture is very similar to New Horizons. Programmatically, we're very similar to Parker Solar Probe. So you'll see those two come up quite often in the coming slides as comparison points that we used for Interstellar Probe. Bottom up is a buildup of labor, parts, and other efforts that kind of exactly what it sounds like. It's an addition. It's an add up of all those things together. It requires a lot of detail, and that's not something that we have yet for Interstellar Probe. Typically, you don't really see bottom-up estimates until around phase A, and right now we're pre-phase A, so that's not something that we've incorporated yet for Interstellar Probe. But that is something that further down the line we do want to incorporate. And then lastly, you have parametric, which is cost estimating relationships. So the use of relating cost drivers to cost. And there's various parametric tools. You have the ones that are developed commercially. You can develop your own CERs from cost data, or there's also the NASA developed tools. So for Interstellar Probe, we have used both commercial tools and some NASA tools. Next slide, please. Okay, so the ground rules and assumptions for the Interstellar Probe estimate. We started with the ground rules and assumptions from the decadal mission studies that happened this past summer and last summer. So what I mean by that is, we had to pick a fiscal year to start with, and we had to start with some set number of reserves in our estimates for uncertainty and cost risk. So we started with those assumptions from the decadal study and then developed our own as we went along. In terms of how the costs are reported out, we follow the standard NASA WBS. So, we have 1, 2, and 3 being PMS, EMA, and so on. For phases A to D, the costs will be reported at the level 2 level of detail. And for the payload and the spacecraft bus, we'll be showing level 3 level of detail. For phase E, we are currently only at the level 1, so the complete phase E level of detail. We don't have like a WBS breakdown for that yet. That is something that we are working on and would like to get to. But for now, based off of the tool that was selected, that we selected to estimate phase E with, we are only at the level 1 level of detail. The other assumption, which Michael touched on earlier too, for the cost estimate is that we've assumed that the spacecraft is agnostic. It'll be directed, but we haven't assumed who it'll be directed to. So it's a directed spacecraft, similar to other large strategic missions, with a competed payload. So the payload will be competed and dispersed with the spacecraft being directed. And again, we have baselined everything in fiscal year 2025 dollars. So everything's on level playing field. Any historical analogies we've used have been inflated to fiscal year 2025 dollars using the NASA New Start inflation indices. The estimate assumes a launch in September 2036. So phase E starts September 2036 is our assumption. And we also assume a 8-year development cycle from A to D. So it's 7 years for B to D and a year of phase A, which Michael touched on earlier as well. In terms of reserves, we have 50% on phases A to D, excluding the launch vehicle and launch services. And for phases E and F, we have 25% reserves. And those come from decadal mission studies, but we also did analysis on our own to see if that would be adequate, which you'll see later on in the cost risk slides that those reserve levels were deemed adequate. Next slide, please. Okay, so for phases A to D, we used a mix of methods in order to develop the costs. We looked at historical analogies from the Cadre cost database and also used 3 parametric models. So the Cadre cost database is NASA's database that contains cost data for previously flown missions of a certain size. So it's a treasure trove of cost data. And for the parametric models, we use Sphere for Space, NICM, which is the NASA instrument cost model, and price true planning. So we varied which tool was used based off of how appropriate it was for each WBS. So not every single WBS was estimated with all the tools. It was, what's appropriate based on the situation. So for example, the NASA instrument cost model only estimates instruments. So that was only used on WBS 5, for instance. Next slide, please. Okay, and then for phase E, we used the Mission Operations Cost Estimating tool. This is also a NASA developed tool, and it covers all of phase E through a defined schedule that was provided by the mission ops people for that phase E 50-year duration. It includes all the costs that you would associate with phase E, so PMSCMA, science, mission ops, GDS, and EPO. It does not include DSN usage fees, since that's historically not captured in the underlying cost data that goes into the MOSET model. And the MOSET model outputs costs as a single estimate at the WBS1 level. So that's currently where our phase E estimate is sitting at. It's at the WBS level 1 level of detail. We also did historical cross checks with New Horizons, Parker Solar Probe, and other similarly large scale missions. And you'll see in the coming up slides that we did that through doing an average cost per year analysis, since they all have varying lengths of phase E duration, with Interstellar Probe being way up there at 50 years. Next slide, please. Okay, so here's our first look at the numbers. You can see that the first blue line there, the subtotal, it's the phase A to D subtotal. So our before reserves, our development costs are $1.1 billion. When you add in that 50% unencumbered reserves that we're holding, you're sitting at a little under 1.7 billion for A to D development. That includes 169 million for PMSCMA, 50 million for science, 361 for the payload, and that's for the notional payload because the payload will be competed. 388 million for the spacecraft, 37 for pre-launch mission ops and ground data systems. And due to the way we estimated that line, we combined those two together. So you'll see the ground data systems line is empty down there. That's because it's included in that 7-9 line. We have 26 million in here for nuclear launch approval. This 26 million was a ground rule and assumption number that was pulled from the decadal studies from this past summer as well. So we don't have a good feel for what that number would be quite yet. We have that 26 in there right now as a placeholder, since that's what was used on the decadal studies. And then we have 95 million in INT. For phase E, that MOSET estimate is 1.164 billion. And with 25% reserves, we have a phase E total of about $1.5 billion. So that is a really large phase E number, but again, keep in mind that's over 50 years. And when we start looking at that at a per year basis, it's not quite as scary as it looks now. It's actually kind of on the lower end of phase E costs, since we spend so much time in quiescent cruise. So when we add all this together, we have a total project cost. So, 8-year development, 50-year phase E of $3.144 billion. Okay, next slide, please. Okay, so we first wanted to see how we compared to other missions in terms of our development costs. So this was our cost benchmarking exercise for development costs for Interstellar Probe. So on the previous slide, you saw that our development cost estimate is about a little less than 1.7 billion, which is more than a Parker Solar Probe, more than the New Horizons, but we have a lot more that we have to account for in our costs to make sure that we're ready for 50 years. And once this thing launches, we don't want anything to go wrong. We have other missions on here that have been we made anonymous for now, since we're not sure if we're able to release that data yet because it is cadre protected data. But these other missions are other large strategic missions. So if you look at how we compare to those, we're actually, fairly in the middle in terms of our development costs. Next slide, please. Okay. And then here's a level 3, WBS level 3 detail slide on the payload estimate. So the first thing to note about the payload, though, is that this is a notional payload. We are assuming it'll be competed, but if these were the instruments that were selected with these capabilities, this is what it would cost. So the way that we want to frame the payload estimate really is, this is the estimate for the capability that we want, not necessarily like these individual instruments, but the capability that we want. So for the capability that we want for the payload, the estimate is 361 million. And this covers just the instrument costs. So the engineering and the hardware, it does not cover the science investigation costs. Those are carried in WBS 4. And again, these costs are all in fiscal year $25. Next slide, please. Okay, and then here we have our baseline spacecraft estimate. So you have the Interstellar Probe baseline estimate as the second column there, that's 388. And then you'll see the comparisons to New Horizons and Parker Solar Probe. So, we're pretty much in between a New Horizons and a Parker Solar Probe in terms of cost. There are a couple additions to the Interstellar Probe estimate over New Horizons, which account for why it's higher than New Horizons, even though we are architecturally somewhat similar to New Horizons. The first being that assumption that the spacecraft is agnostic. So we have a spacecraft PMS-EMA costs associated with the Interstellar Probe estimate that are not seen on New Horizons or Parker Solar Probe, since APL as an organization usually carries that cost elsewhere. And if you go through the different subsystems, and we'll see what those costs are too. The RTGs are carried in the EPS system, so that's why that number is so high. And rest of this is pretty straightforward in terms of spacecraft hardware. The Interstellar Probe estimate was estimated using mostly analogies to past missions, so it accounts for a lot of historical development risk on the spacecraft as well. Again, this also only covers WBS 6. It covers nothing else except for the spacecraft development and engineering, and the costs are in fiscal year $25 as well. Next slide, please. Okay, so cost benchmarking for phase E. So at an average cost per year basis, Interstellar Probe is only running around 22.7 million per year. It's highlighted there in orange. So we're actually on the lower end of what we expect, or what other large strategic missions have spent for phase E. And separate from the phase A to D cost benchmarking, this was actually pulled from the Planetary Society cost database, which is public information. So that's why you have all the mission names here. But if you compare Interstellar Probe to Cassini, what's planned for Clipper, the early years of Voyager, we are much less than what those are going to cost or did cost. In terms of cost per year, we're kind of in between the Parker Solar Probe and a New Horizons. So it's not as big of a number as it looks like at first. So I mean, over 50 years, it is a pretty large number, but on a cost per year basis, we are actually on the lower end. So that's kind of the main takeaway from this is, it's not as scary of a number when you start kind of digging down and analyzing what it actually means. Next slide, please. Okay, so this is the cost model results for the tool we ran for phase E. So again, like I was saying, the average cost per year for phase E is 22.7 million, and that's for that 50 years, over that 50-year duration. On a per month basis, that's around 1.9 million. And if we look at it during quiescent cruise versus active cruise, it's about 2.8 million during active cruise versus 1.8 million during quiescent cruise. So, there is fluctuations that go into that 22.7, but, overall it is 22.7 average. And then on the right there is the model output for MOSET. So you can see what those fluctuations actually look like in terms of the various activities going on during phase E. And then all of that rolls up at the bottom to 1.163 billion for 50 years. Next slide, please. Okay, so this is the cost risk analysis that was done for phases A to D. So cost risk for development is something that we're pretty familiar with in terms of how to handle it. So, the uncertainty, the problems that arise when you start integrating hardware together, those are things that we've seen over and over again on, multiple missions, and it's something that we know how to frame and quantify. It's compared to phase E, which you'll see next, it is technically higher risk, but we know how to work with it. So before reserves, the cost risk analysis has the estimate sitting at the 41st percentile. After we add in 50% reserves, that puts us at the 68th percentile in terms of how confident are we that we can complete this with the resources that we've estimated. 68th percentile for this kind of stage in the game at a pre-phase A level, we're usually want to be around 50 to 70th. So being at 68% is very comfortable. And as we get more detail and we continue working on this, we can continue to refine the estimate. But 68% for an estimate pre-phase A is kind of where you want to be at. Next slide, please. Okay, so before I go into, sorry, now the slides are going, okay, yeah, here we go. So before I go into the phase E S-curve, we have a short discussion on kind of how we handled phase E cost risk. So it's different than anything we normally do. So first off, we don't normally run cost risk on phase E, since for the most part, it generally is a low cost risk, low cost risk element. A lot of phase E, you don't have any development going on anymore, and development is usually where your risk is. It's mostly just level of effort and how level effort, and there's no schedule risk in phase E for Interstellar Probe. So overall, phase E is actually, in terms of risk, cost risk on the estimate, lower risk. So how did we quantify risk during phase E? We're not in the place yet where we can do a BUE since we don't have enough detail yet. So we ran MOSET. And what this means is because MOSET is based off of historical data, it already includes the historical costs of risk. So all of the missions that are in that underlying data set, what they experienced in terms of cost growth and cost risk, that's already baked into that estimate. So we didn't want to double count cost risk in phase E, but we also wanted to make sure that we were incorporating uncertainty and challenges that would be unique to Interstellar Probe. So what risk will Interstellar Probe face during phase E? So cybersecurity being one of them. That's kind of more relatively recent risk during that we see during phase E that some of the older missions in the data set may not have had to account for. Unexpected environmental challenges. Once that it's 50 years is a very long time to expect that something out there won't go wrong. We've also included risk for design error and then also for science team instability. So 50 years is a very long time to keep a team going, especially a team this large, since, as you saw on the payload slide, there's a lot of instruments that are on that notional payload. So the science team, as a consequence, will also be really large. All of these risks feed into a very, very rough risk analysis that we did on phase E to determine whether or not 25% reserves would be sufficient for Interstellar Probe. Next slide, please. So as you can see here, it was deemed that the 25% reserves that we've included for phase E is sufficient. The MOSET estimate again was $1.164 billion. That falls at the 23rd percentile of the phase E S-curve. But once you add in that 25% reserves, that puts us at 1.455 billion, and that has us at the 84th percentile of the phase E S-curve distribution. So that's a very good place to be in. Next slide, please. Okay, so other things that are cost drivers for longevity that Interstellar Probe has to account for that other missions previously haven't had to account for, which is, part of why our costs are kind of what they are. Include a mission librarian, a technology maven, science archivist, and multiple people in the same role in terms of management to make sure there's a consistent flow of knowledge for management of the mission, and there's no kind of breaks in that. There's also ground data systems that will need, ground data system upgrades that will need to account for space segment engineering. This next bullet also is very important. Archiving, data storage, and record retention. Making sure that all that's available over 50 years and doesn't get lost somewhere. And navigation, mission design, and ground communications infrastructure will also change over 50 years. So we want to make sure that we have a plan in place that, all of that can be successful. Next slide, please. Okay, so this is my last slide, actually. So what things do we still need to account for, or not account for, but what things do we want to get a better understanding of for the Interstellar Probe estimate? So some of the things that we're looking into deeper is the development of high fidelity software only simulators, because testbed hardware that's going to last for 50 years is hard to come by. So we want to do a formal trade study to see if the cost benefit of developing that software only simulator is worth it. We also want to get to a point where we can do a higher fidelity estimate for PMS-CMA for Interstellar Probe, so that it better aligns with the expected mission requirements. And that's typically something you see happen kind of in a phase A study where you have enough information to start laying out like a labor profile for a PMS-CMA versus estimating it via a cost estimating relationship. We also want to look at nuclear launch approval costs. So right now, again, we're using a 26 million placeholder that we pulled from the decadal studies. But what we've seen is, or our first glance is that from looking at past missions, it might be low. Nuclear launch approval historically looks like it's been a little bit higher than that 26, but we need to get more confirmation on that. We also want to better incorporate the cost of longevity. So all those cost drivers on the previous slide, we want to be able to better incorporate those into the estimate. So we have that incorporated currently, but obviously as we get more detail into how each of those roles and situations might work, we can update the estimate so that it does a better job of incorporating longevity. And all this is to say that we're continually updating the estimate and our estimating methodologies based off of new information that the team provides, or when we start looking through data, if something points us in another direction, we're always iterating through the estimate. So this is probably like I've lost count what iteration we're on right now, but it's been an effort. So with that, I think we have 8 minutes for questions.
Thank you, Kathy. So we do have one question in the Q&A tool already. Marshall asks, after 1 decade of interstellar probe mission navigation and data downlink is likely to shift from the Deep Space Network to the NRAO/Next Generation Very Large Antenna. Did we take into account this change? No DSN charges, but NRAO charges. And did we talk to them about how to cost this? In particular, they're going to want to get paid, whereas we do not, under the mission costs, pay the Deep Space Network for their time directly. NASA pays for it, of course, but the program doesn't.
Yes, so that's not included currently. So since we haven't included any DSN charges, any switch from DSN to something else has not been included. What is included is just what the program would be paying for phase E.
Very good. And we've talked a little bit about international contributions or collaborations on this mission all along, and I believe, showed a fair amount of that over the course of the last week. But I would say that there are other areas where international collaborations, instruments perhaps, or other things could be realized. But we've talked a little bit about could other nations that have downlink assets be brought into the mix as well. And so paying for these things directly are not necessarily the only way to do it. If another nation had an asset that we could use for downlink, perhaps there could be a fair trade of their scientists being on the science team, their scientists being a part of the earliest publications of the data that's returned from the mission as a whole, and not just through their ground station, of course. And so, though we don't have an estimate directly from a group like that, it's certainly an area that we need to pay attention to. So, any other questions for Kathy? Any other questions for cost or how we went about trying to break up all of this into its parts and put it back together again and find a dollar sign to stick in front of that number? All righty. With that, thank you, Kathy, very much. It's great to see the rigor that's going into this alongside the technical rigor and the scientific outlay of what the mission would do. I really appreciate it. You and Sally and Larry have done a great job pulling all this together. Thank you very much.
Thanks.
All right, everybody, we're going to take another break. We'll be back here at 11:20. Clay Smith is going to talk to us about longevity. That's been a very important and ongoing effort on this study to really get our arms around what it's going to take to do a mission that that lasts as long as this one should, as well as what is it going to take to convince the community that in fact we can do a mission like this. And the findings so far have been quite compelling. So we'll see you all back here at 11:20. Thank you.